All right, so for my presentation, I'm going to focus on HyperXpert, which is a new tool. And later today or tomorrow, Jet Zero Logan is going to be talking about how that was used on the Jet Zero project. Those that are familiar with our software are quite aware that as we would size this 737-like wing, even though we have an eye-shaped stiffened panel on either side of that rib, they're like neighbors, right? The way that the software would optimize potentially is to come up with a compact section on the left, as you see there, and then and even though it may have the relative same area, the same kind of mass, it's a vastly different design. It's slender, right? It's taller. And the issue with that is manufacturing. It's a challenge then you can't take that to your designer, or you can't go to the factory floor and say, make me this stringer. And this problem is actually continues. If it were composite, the challenge would be, what mandrel do I come up with for my tooling? Because you don't want this variation in your tooling that you are using to lay down the composite. In addition to that, you have all these ply drops and adds going from a very thick laminate to a very thin laminate. So this is kind of where we are in our optimization when you run HyperX today, for the most part. And we all know we want to come up with a solution that's more like this, right? So the stringers are more uniform and cross-sectional dimension as you go from root to tip. So again, HyperX today, when you run it, if you're not careful, you may have a solution that looks like the top, and you want the one on the bottom. This is the HyperXpert roll. We often use the UAM as basically urban air mobility application as eVTOL, electric vertical takeoff and landing. And we are able to import CAD now, so the CAD and FIM are shown together here. The mesh lines are off, but you're looking at the zones, the property zones, the color pattern representing the underlying rib and spar configuration. Now, if you were to take this vehicle and rotate it 180 degrees and you peeled off the upper skin, you would see something like this. You would see the underlying ribs and spars. What we want to do is to evaluate 4 different kind of possibilities. The top one is, I think that's a 2-spar 7-rib design. The bottom right is a 3-spar 13-rib design. And you can see the other two, a combination of that. So what I kind of want to do is to do a little challenge problem here with the audience, and that would be, you can keep it to yourself because there's kind of a lot of people here, but which of these do you think will be lighter for that wing? In addition to that, it's just not the layout of the substructure, but let's also consider the possibility that one design is hat stiffened, the other sandwich. And the sandwich in this case has a thick OML, as we traditionally do for damage tolerance. So anyway, there's 2 of these guys, and there are 4 of these guys. So there's 8 total combinations. So what I would like to have you kind of play a game with yourself is, which of these architectural layouts with which panel concept would be lighter? And so kind of keep that in your mind, and I'm going to continue on. The thing about the manufacturability is the sandwiches have fewer variables than the hat does. The sandwich has your typical face sheet thickness and material or laminate family. It's got a core material, which would be the core thickness and different kind of core densities. The hat, on the other hand, has a lot of variables, right? It's got variables for the height, the widths of the flanges and the crown. It's got variables for that angle you see there. And additionally, you could have different laminate thicknesses for the different regions of that blue part. So the web and the crown can be different actual laminates. So a lot of variables here. That's the challenge. And when I say that we want to do, tell you the lightest weight design, we don't want that academic, lightest possible weight. We want a weight that represents something you could actually make, as you see in this PowerPoint slide here. So every one of those colored stringers is a different, potential size, but we really want the profile shape to be constant. So it would look like that. If you looked at it from underneath, you would see that. That's the weight estimate we want for the hat. And when we're talking about the hat weight, we're talking about not just the skin, but also the ribs and spars. So in this scenario, we're optimizing hats for the different substructure. And you can see the rib that has the engine mount has a stouter looking hat cross sections than the other ribs do. So with that, I will do a live demo, but before I do the live demo, I want to introduce another example, and this one is where we're considering post-buckling of the skin. So for instance, a mode shape could be as you see here, or the mode shape could be something similar to that. And what we're wanting to know is what would be the optimum spacing of this panel when you consider different variations of post-buckling. So we let it post-buckle at 50% limit load, 100% limit load, and 150% limit load, which is actually ultimate. And we're wanting to know that, but we're also wanting to know that in relation to what's the optimum spacing in that scenario. So I will now go to the software, because I always love doing live demos. So this is the finite element model with the mesh shown, mesh turned off. And under the result tab, there's a thing called HyperXpert. And it has this on form. I can hit the green plus, sort, and I'm going to select those 8 combinations as you see here. So the S2, R13 hat, and so forth. And I say OK. And so when this comes up, you can use this tool here to automatically put the data in the right frame. And you're looking at, on the left, a weight axis, and the bottom is variability, or the actual number of variables. So if I go all the way to the far right, you can see a point here. And I guess the cat is out of the bag, because the lightest weight, as you may see now, is the 2-spar, 13-rib architecture with a hat, weighing 115 pounds, 0.6. Let me also bring to your attention, this is what we call an anchor point. So this is the lightest possible design. This is where you allow every panel to be what it wants to be. And Logan's going to be mentioning in his presentation anchor point, so kind of remember that. And so you see a lot of gray points. Basically, it's saying these are unidentified right now. And so we could come over here to the software tree, and we can look at identifying. If I click that guy there, that blue means identify all the points that are sandwich. So these are the red, the sandwich points. I could also identify the hat. These are your hats. So again, that's the same point you saw earlier. So now we're curious, what's the lightest weight sandwich? And it happens to be at 144 pounds. It also has, I think I'm missing the wrong one there. Yeah, this one has 7 ribs instead of 13 ribs. So that's 144 pounds. And this is also the anchor point. So we can hit this button to put it back in perspective. And I can come over here and I can do the same thing by identifying all the run sets. And let me go ahead and just include these guys here. So you're looking now at 8 items in your legend, right? And it's a little bit complicated. So I can come over here and I can turn off the hat and be able to look at just the 4 sandwiches as you see here. Or I could likewise turn off the sandwich and then look at the 4 different hat designs as you see here. And you notice that the bright green with 2 spars and 7 ribs is considerably heavier than the one with 13 ribs. So that's pretty much the end of this first example I wanted to show. It kind of gives you a taste of what you can do with the software. Let me go back to the data selection, and this time I will select the 3 different analysis criteria options with 50, 100, and 150% limit load buckling. Notice I am choosing the 2-spar 13 rib design with hat, so I'll say OK. And in this case, we're just looking at the skin. And again, you see a lot of data points for this. And I can identify right off here, identify the data. And you can see here, I don't know if it's easy to see that red. You can see the difference between the red and orange. So the red is at the bottom. And without, much, kind of like you anticipated, post-buckling is a lighter design, and this is how much lighter it is for the number of variables. And one way you can see variables, I can identify, and additionally, at the same time, the spacing. So I'm identifying 3 different criteria and 3 different spacings. 3 times 3 gives me 9, so we have 9 items in the legend, and you can see all this information here. Now I know, sitting in the audience, not driving the software, kind of hard to distinguish what you're looking at, right? So let's simplify this. Maybe you are interested in the function of spacing. So what I can do is choose spacing as my bottom axis here, and I can have these points shown. I can turn this to identify off because we already know by the axis what it is for spacing. And now this is maybe a little bit more useful because now you're looking at the function of weight in terms of the bottom axis spacing and also in terms of the analysis criteria. To further simplify, I can turn off all those other points. These other points represent data that are relevant. They all have positive margins of safety, but the Pareto frontier is showing you the lightest combination that you probably are really interested in. So I can turn off the other data points and just look at it in this fashion. So to kind of end, I just got that red light, is the 50% design is lighter, but you can see relative flat line or insensitive weight growth going from the 3.25 to the 4.33 inches, and a slight weight growth when you go to the 5.41. Let me isolate the other extreme. So I turn these guys off, and I just look at, that was the wrong one, this one here. This is the scenario where you're requiring it not to local buckle until you reach ultimate. And you can see here that it's highly sensitive to the spacing as well. So the tool then has the advantage of helping you decide what manufacturing dimensions you want to hold constant, but it also gives you the visibility into the impact of different choices you make in your analysis criteria and trade-offs between how maybe ambitious you want to be with how deep you want to go into post-buckling maybe, and how that would help improve manufacturing by having further spaced stiffeners. So I think with that, we're running a little bit late, and I did kind of cut it short, but it was meant to give you guys a teaser. We are intending to have a workshop, basically hosted, I guess, through some kind of web service so that anybody can see it at your home office. And in that workshop, maybe get in more detail. Also, for those that, you know, would like to learn more, we can also set up a Zoom or a Teams meeting just between our company and your company, and spend about 2 hours to give a real deep dive into this capability. So with that, I will stop. And I don't know if there are any questions. If so.
So you're, it's louder than I thought. It's all based on designing for the lowest weight solution. Is there a way of designing for lowest cost?
Well, cost is something that we are not familiar with. We don't know, we're not an OEM, so we don't have cost data. But what we do have is, again, the ability to look at the prismatic nature, you know, the constant cross-section. We do know what you can tool. You know, we know what, like for stiffened panels, because we do work the NASA HiCam project, high-speed composite manufacturing. We do know that manufacturers, one of the first things they need to freeze would be, if it's a hat, it's got to be the angles here, right? The second thing would be the width of the crown. The third thing would be the height. And so they have their pecking order and what variables they want to hold constant, right? And that is what we're providing our customers, that information.
Is there a desire to add stiffness as a criteria instead of, say, weight?
You mean?
So
Well,
if it's, say, more like a flutter problem and you need to drive towards a certain stiffness for lowest weight or design parameters?
yes, there are presentations this week that are going to be talking to that issue. And for one, we have one from Jet Zero on Aeroelastic Solution 200 coupling with HyperX, for instance. We have another one where we're coupling the FEA eigenvalue buckling and frequency as well. So these are all stiffness-related type criteria. All right, I think I probably should sit down now. Oh.
Yeah, Craig, I was wondering, you know, with more parts, double the ribs and the hats, is there any way to take into account like the extra weight from the joint, like having to protect the carbon or fasteners or anything like that that would kind of add into having more parts and a higher weight associated with that?
Well, we are looking into doing like we have this sort of, I haven't used this term in a while, but it was like a multi-phase process where we learn from our customers they want to first establish the acreage, right? And generally speaking, they want that to be what it wants to be. And then they go in there and they size the joints, and you know, they want to do that where they don't have to add material. But you know, if they can't get a fastener pitch or size that satisfies that, then they do the local pad ups at the edges, at the bands of the panel. And we do have a way in the joint sizing code to take the acreage and to let that be the beginning of the necessary laminate thickness, and then we add plies to that as necessary, like if it was a bearing bypass or a bearing issue with a fastener. That's kind of how our software is set up to handle that, to do a localized sizing in those strips, the bands. August? There he is, okay. Yes.